So I've been looking for all of my high school career. I've been looking for an opportunity exactly like YRI, where they just take your passion for research, just your idea and motivation, and they give you the opportunity to really apply it in a actual research project with an actual research mentor. Like my mentor, Dr. Pullela, she was very experienced, multidisciplinary PhD, and she gave me a lot of guidance in sort of the research process, how to format the data, how to make the model understand how it works. So overall, I'll give YRI a 10 out of 10. I would really appreciate the opportunity. Today, I'll be discussing my project on machine learning-driven classification of agricultural pond biogeochemical signatures for environmental monitoring. It was done by me, Sricharan Pullela, and I was mentored by Dr. Parimal. So this is a quick overview of the research process. So the data collection was done in a parent study in Georgia, and we took this data and we created the model, and we predicted the dissolved organic matter DOM indices, and then we produced the statistical results and analyzed the output, and then we analyzed its applications in real life agriculture and how it's applicable in water quality management and helping environmental sustainability. Today I'll be talking about our work on developing machine learning models to predict key dissolved organic matter indices. These were mainly BA, freshness index, FI, fluorescence index, HIX, humidification index, and BIX, biological index. And these indicators give us the insight into water quality and ecosystem health. Beyond predictions, we also identify the biogeochemical drivers that influence DOM fluorescence, which helps us understand the underlying processes. By applying these ML models, we were able to actively monitor and manage the irrigation pond water quality. And this is especially important for agriculture. Farmers say they need to monitor the water quality of the pond irrigation system before they use it in their crops. And overall, this research helps close critical knowledge gaps in carbon and nutrient cycling, and this provides scalable, sustainable tools for agricultural water management. So a quick background for how the data was collected. From October 2021 to October 2023, this data was collected at the Tai Tai Cooperator Farm North, or TSFN, and Tai Tai Cooperator Farm South, TSFS, and the Sumner Cooperator Farm Pond, SCF. So 3 different ponds, and these sites were chosen to capture the temporal variability in the pond chemistry and dissolved organic matter composition across multiple seasons and agricultural cycles. We monitored this data was monitored over 2 years. Researchers were able to observe both short-term fluctuations and long-term trends. And the chemical measurements include a wide range of elements from say aluminum, arsenic, boron, calcium, iron, potassium, many others. There was around maybe 30 to 40 nutrients and data points collected per day. And then tracking these metals and nutrients was important because these influence water quality, they influence the plant uptake and microbial processes within the ponds. And for example, the iron and manganese, they affect redox conditions, while the elements like potassium, calcium, they play direct roles in nutrient availability for crops. And in addition to the elemental concentrations, we also measured the UV absorption at varying excitation and emission wavelengths. This technique provides information about dissolved organic matter quality, and this can be linked to its source and reactivity, specifically with the UV indexes. By combining this chemical data with the optical properties, we gained a more complete picture of how the pond ecosystem functions over time. And ultimately, this data set gave us a clear evaluation metric for how we were going to make the ML model and predict the DOM indexes effectively. So for methods, the researchers that collected this data and made the original parent study, the DOM optical properties were analyzed using EEM, excitation emission matrix fluorescence, and spectroscopy with a HRIBA scientific aqualog spectrophotometer. And this provided high resolution spectral profiles of the pond dissolved organic matter. And then there were, of course, the 4 indices. The freshness index reflects the contribution of recently produced, easily altered organic matter. There was the fluorescence index, which distinguishes the microbial versus terrestrial sources of DOM. There was the humidification index, which indicates the degree of humic substance accumulation, and this is linked to terrestrial and decomposed material. Then finally, there was the biological index, BIX, which highlights the contributions of microbial and autochthonous production within the pond ecosystems. So for data cleanup, there was not many variables we had to remove. We had to mainly remove 3 and alter 2. The flag, date, and station numbers were all removed because they didn't directly contribute to the DOM index or any element concentration for that matter. And then we also had to change the site and habitat because those weren't numerically represented. So we encoded site as the SCF was 0, TCF N, or the North Tai Tai Corporation Farm, was 1, and the South one was 2. And then the habitat was littoral environment was 0, and limnetic was 1. So this ensured the consistency in model outputs, gives a clear metric for the ML model to use to evaluate the DOM index and predictions. And in the end, there was also the abstinence 254, peak C, peak M, peak B, and peak T. These were all UV absorption indexes, and these were all removed because of redundancy. So all of these, when we created the correlation plot you see on the right, we correlated all these every element other than the DOM indexes with each other, and we found that the 5 listed on the bottom, they had much higher correlations, over 0.85, with many of the other elements. So therefore, these indexes, they would create redundancy in the ML model. Therefore, we have to remove them to reduce that redundancy, which would enhance the performance of the model. So we used two main models. We used random forest or RF, and we used a GBM, gradient boosting model, two different ML models, to predict the DOM indexes, all 4. And we used metrics such as the coefficient of determination, the root mean squared error, RMSE, and the mean absolute error. And when we took all of these, we compared the validation metrics for both models and testing metrics for both models. And RF, originally for validation metrics, it did pretty good. It was above 0.88 for all DOM indexes for the coefficient of determination. But then eventually, when it came to testing, these numbers all dropped below 0.9, which in comparison to, which first of all, it shows a bit inconsistency in the prediction potential for RF. But then when we compared it to GBM, we found much more promising results, where the coefficient of determination stayed above, originally was above 0.9 for 3 out of the 4 indexes. And then at least 3 out of 4 indexes were also stayed above 0.9 for the testing metrics for the GBM model, and the lowest was only a 0.8. All others were above 0.91. So this showed us a bit more consistency in the results, and we felt this made the GOM model a more promising method, or more promising model to use in predicting the DOM index values. And so for results, again, the GBM was the main model selected, and we produced the correlation plots comparing the actual versus predicted data points for every single index, which you see on the right. And it clearly showed that the accuracy of the model was quite high. The evaluation plots highlighted in this strength, showing very high promising outcomes. And they had a correlation coefficient of at least 0.9 for all of them, and above 0.96 for 3 of them. And this showed the very strong performance of GBM as the best model for predicted analysis. And then we also made the residual plots, which showed all normal distribution. So any errors were likely due to random chance for any index. And then results for the SHAP. So this was produced to check for the most critical predictors of the DOM indexes, and it revealed a clear hierarchy among the predictors driving the DOM index matter. And the primary predictors were potassium, strontium, and peak A. Peak A was the fluorescence, and it was similar to the other peaks that were removed, but we only did one of them. So we kept peak A, which was the fluorescence intensity at an excitation wavelength around 260 nanometers, and the emission wavelength around 450 nanometers. Then the potassium emerged as the strongest positive but also inhibitive driver specific to each index, and this in contrast was compared to strontium and peak A, which were also primary indicators. They tended to have mainly negative effects, indicating that the increases in these variables generally suppressed DOM index values. And then there was also many secondary predictors that play a more moderate index specific role. For example, there was phosphate, phosphorus, magnesium, chloride, sodium, sulfur, and all these showed measurable influence, although the effects were less consistent across in each index, and again they were specific to certain indexes. And these predictors often acted in combination, shaping certain indices more than others in the universal control. And finally, most of the remaining variables, particularly mainly optical metrics and the trace metals, they were clustered near 0 in the SHAP space. And this clustering suggests their low contribution and they were not central to the model performance. So the key takeaway here would be that the DOM variability is largely governed by relatively small set of influential drivers, rather than like a full suite of measured chemical and optical parameters. And this finding highlights where monitoring effects should be more focused on. So discussion are, so the model performance analysis. So again, the GBM showed clear outperformance over RF, and the model achieved particularly high accuracy for the spectral slope parameter, the freshness index, BA, and the biological index, BIX. Both are R-squared values above 0.94, and this indicates effectiveness of GBM in the DOM signals tied to microbial activity. However, the performance for freshness index, FI and humidification index, was more variable in comparison to the other two indexes, and this is particularly shown in both validation and the testing datasets. This variability reflects the strong influence of local and seasonal conditions on the DOM composition in pond ecosystems. And when examining predictor importance, the relatively small dataset was shown as being more important over others. Potassium, which was the spectral slope ratio, and the peak A were the dominant predictors, while phosphate, phosphorus, and other trace metals were shown as secondary or not as relevant. Despite these strengths, however, there were some limitations of the model. So for instance, the model did struggle slightly more with the HIX and FI, where there was more sensitivity to the site-specific drivers and reduced generalizability to most of the ecosystems. And additionally, there was collinearity and context-specific, context-dependent predictors, such as the nitrates and certain optical ratios, which further constrained the performance across the specific sites. And then ecologically, the findings provide new insights. The potassium and strontium ratio enhanced the humidification reflected in higher HIX values, while it simultaneously suppressed the freshness index. These variables, they influence the microbial versus terrestrial balance of the DOM, which was captured by the FI and BIX. And such insights are valuable for irrigation and pond management because they highlight which chemical and optical signals best reflect shifts in DOM quality. And overall, this study demonstrated that machine learning can not only predict the DOM indexes with high accuracy, but it also uncover mechanistic relationships that inform sustainable water quality and management in the agricultural systems. And one of the most important outcomes of this work is just the show of application of ML in agricultural water management with this specific model. It allowed us to move beyond just static sampling and like direct pond activity. Instead, it moves towards real-time monitoring of the pond ecosystems. So, for example, these models can serve as early warning systems which detect nutrient loading and pollution, organic pollution, and the shifts in DOM composition before they escalate into higher water quality problems. And this proactive detection is especially valuable in the farm ponds where nutrient inputs and runoff can fluctuate rapidly. The predictive insights also directly support the management decisions. It identifies the key chemical and optical drivers of water quality. And this model helps guide interventions such as adjusting irrigation schedules, improving filtration systems, mitigating runoff for in the field, or fine-tuning fertilizer application and timing to reduce excess nutrient inputs. In this way, the model acts as the nutrient support tools, and it links the biogeochemical understanding to practical on-farm management. And another benefit lies in proactive water quality at a broader scale, integrated with more high like C2 sensors, which would be remote sensing or UAVs, or even satellite observation. The model shows a high resolution and the regional scale monitoring, and this enables rapid response to water quality concerns before they impact crop productivity or ecosystem health. And finally, the model contributes to resource and infrastructure optimization. It reduces the reliance on frequent manual sampling and laboratory analysis. This lowers the costs, increases efficiency, and extend the lifespan of the irrigation infrastructure, and promotes more sustainable use both water and nutrients. And taken together, these applications demonstrate how ML models can provide scalable, cost-effective solutions that strengthen the resilience and sustainability of agricultural landscapes. So in conclusion, this study predicted the DOM indices, FI, HIX, BIX, BA in agricultural ponds, and it used chemical, optical, and elemental data as the data used for predicting the DOM indexes. And these key predictors, such as strontium, potassium, and peak A, sulfur, reflected the process of nutrient cycling, mineral inputs, and microbial activity in these ponds. And these models revealed biogeochemical patterns distinguishing humified versus fresh microbial-derived DOM under shifting conditions. And importantly, this approach enables rapid, non-destructive monitoring of the nutrient enrichment and this runoff and microbial growth. And by integrating this machine learning into water quality management, agriculture gains scalable, cost-effective tools for adaptive decision-making and anticipatory stewardship for vital pond water resources. So YRI, it really gave me this opportunity. So I'm a senior in high school right now. So I've been looking for all of my high school career. I've been looking for an opportunity exactly like YRI, where they just take your passion for research, just your idea and motivation, and they give you the opportunity to really apply it in a actual research project with an actual research mentor. Like my mentor, Dr. Pullela, she was very experienced, multidisciplinary PhD, and she gave me a lot of guidance in sort of the research process, how to format the data, how to make the model understand how it works. So overall, I would give YRI a 10 out of 10. I would really appreciate the opportunity. Some of my best moments, I would say the first sort of like aha moment was when the model first gave results, and at first it was like all above 0.8. Is like because environmental ML is very inconsistent almost, because the indexes and elemental values they change across many sites, so it's hard to predict them. So when you have like that sort of moment where it's like, oh wait, these indexes, this model actually it's pretty high accuracy, it's working, it's doing what you meant for it to do. It's sort of just like that nice sort of like validation that you were looking for when you were making the model. And it made me more confident in my work, and it was sort of like the build-up moment before I realized this project was actually like it could actually make it in like a substantial journal and have substantial impact. So obviously, I'm planning to do research in college as well. This experience gave me was very valuable to me. It gave me a great understanding of the whole research process, starting from conceptualization of the idea, applications, and then eventually the paper production, writing out the paper. And it gave me a lot of understanding of data analysis and how to come up with my own understanding, interpretation of the data, and then correlating it directly with the real world. Because obviously, this research, it's meaningless if you can't use it in the real world. So this impact of connecting it between what I found and what I made to agriculture, and sort of this like realization that this is actually a very impactful tool that can help most anybody, any agriculture, any farmer, or any person who works in agriculture in the world. That is very useful. So I keep that in my mind whenever I'll do research. For now, it's just like this idea that my work, it contributes to, it's sort of like generating knowledge for people in the real world to use.